Thank you so much for your time. So we are going to present for you the machine learning based static malware detection in our project of Quantic project. So the one who are going to start, my name is Marie Grace. So we are going to start from the problem statement. So we have the core problem our project solved, malware and a good way, and why traditional detection falls short. So before maybe we get into our solution, let's ground ourselves in the problem. Malware is any software designed to harm a system or data. So on other side, the goodware is legitimate software. So traditional antivirus tools are reactive, and our approach is early detection before execution using static analysis. We came with the problem objectives. So we have the machine learning classification models and performance and deployment and implement and CI/CD pipelines. We automate testing on deployment on implementing CI and CI/CD pipelines. We automate testing and deployment workflow. Now, so we have the 50,000 sample of the file for the portable executable file record. So also we have the 27 features extracted from the file headers. So we have also the binary target where the label 0 is a goodware and the label 1 is a malware. So portable executable is industry standard Windows executable format. KUSI continue.
Okay, thank you, Grace. So I'm Daniel, and I'll be handling the data preparation that is from slide 5. Okay, the data preparation. So as you can see, 80% of the data is categorized into training and 20% is categorized into the testing. And during the data clean, we drop some fields those are the unique identifiers and complex test fields that could prevent the model from, in order to prevent the model from memorizing specific files, to prevent overfitting. And we also did some feature coding that is such as the fields that include the magic and the portable executable type, the P type. They were converting to numeric codes during the cleaning stage using factor labeling and also to ensure compatibility across models also. So this help to maintain uniqueness, but then also, as I've already talked about, we utilize 80% for the training and 20% for the testing. Also make sure that there is a balance in the data, and also make sure that there is a data integrity, and also we also handle the scaling and pre-processing. So the stratified sampling on the label column was done to ensure that both the training and test set data maintain the same ratio of malware and goodware, I think, accuracy. Yeah, so let's move. So these were the various models that we considered when we were training the data. So basically, I think there were about 7 of them. And so basically categorized, and we have the linear and the baseline models. We have the ensemble models. We have the advanced boosting models. And also we have the neural networks. So the linear and the baseline will have to do with the logistic regression and the decision trees. And also we also have the ensemble method that has to do with the LG boost, the light GBM boost, that had to do with the random forest and extra trees and the light GBM. MLP. So each model was wrapped in a custom pipeline. The logistic regression models included the standard scalar, while the tree-based models used raw feature values. So now we go to the evaluation strategy. So the strategy for the evaluation was the temporal cross validation, and this was to make sure the validation is robust and also performs well, because we can't rely on a single training pass. So we use the stratified k-fold with 10 splits to generate a robust mean performance estimate, and also standard deviations, which are very important metrics in knowing the best performance model. And also the primary metric was the area under the curve, which measures the discrimination across all thresholds. And that one was prioritized because it measures the model's ability to distinguish between classes regardless of the classification threshold. Then the secondary metrics also have to do with the accuracy that is the percentage of correct classification, then the model selection, that is after the training, we select the best model based on the area under the curve score and also the accuracy, then the standard deviation, the results in the final model selection. So after the training, we realized that LightGBM was the best performing model among the selected models. It had AUC value, the standard deviation was also unique from the other ones. And also, when you consider the parameters and tuning, then you realize that even the basic parameter tuning, the LightGBM performed much more better. Though if we had tuned the other models also, they also do good work, but given an optimum assignment, they perform very well. When we also consider the neural network, we realized that the PyTorch couldn't perform as expected initially, because it didn't really do well with tabular data. But when it was tuned off, it was able to perform better, but it didn't really outperform the rest. It also increased the latency of the training.
Okay, thank you so much, Daniel. My name is Olusegun Banji. The web application was built with Flask, lightweight Python web framework for rapid deployment. It's ensured that we could input values manually for instant prediction. We also implemented CSV upload for batch predictions from uploaded files in just a single step. And we also displayed the predictions in terms of malware goodware. And the results displayed the accuracy and the area under curve. We hosted this website on Render, and it is publicly accessible on the HTTPS link or URL. And this URL is kept alive by a keep alive implementation, which we use to keep Render always alive. And then we also had real-time predictions so that predictions can be made in sub-second. We had CI/CD pipelines implemented. We had our GitHub Actions automating every push by running automated tests, smoke tests, and integration tests. And we do not deploy unless the code that was pushed to the main branch is able to pass all of these tests. So we'll go into the demo of this application. I'll show you manual upload, metrics visualization of both manual upload and file upload. All right. Okay. So here is the application we built. It's having a very good UI. You can just fill demo rows, and it is filled for you all 22 rows, and you can decide to predict malware status. What does it say about this? It says it's a goodware, shows us the accuracy and AUC. And also, you can clear the form after prediction and before prediction. You can also do batch uploads. So for batch uploads, maximum uploads file is 5 MB implemented backend and frontend. So you can upload and analyze the whole of this data. And the results are in that table. We have 32 malware and 1 goodware. The result page is paginated for 20. And also, this application would also show the accuracy and AUC on the results page. So that's how good this application is. So challenges and learnings from building this website. We had to avoid data leakages by strict separation of feature engineering and test data. We implemented hyperparameter tuning, and in doing that, we used tenfold cross-validation. We also implemented the deployment and had challenges like containerization and environment parity issues. We also had some CI/CD implementation and setup done, runner environments, rollback strategy, configuring secrets, and we were able to keep the page alive. In conclusion, we implemented end-to-end ML pipeline from raw data up to deployment. LightGBM delivered the highest AUC and accuracy metrics. Production-ready system was hosted on Render Cloud with Keep Alive implemented. Full CI/CD via GitHub Actions were implemented for automated quality gates. Thank you for your time.